Log on, tune in, find out. Another good idea from Cambridge.
So there's been a tiny bit of progress in recent years on some problems in high-dimensional convex geometry. And my goal in this talk is to present some of the methods that were used. So we're not going to focus on the phenomenology, on the results, but more on the tools that were used in the study of distribution of mass in high-dimensional convex bodies. So this talk might be a bit technical at some points, and I urge you to stop me at any point and ask questions if I'm getting a bit too technical. All right, so what are the problems that still remain in high-dimensional convex geometry? So one of the most famous questions is the slicing problem, which is a question that was suggested by Bourgain in the 80s based on his work on the L2 maximal function inequality, which is the following question. Suppose you have a convex body K in Rn, whose volume is 1. Does there exist at least one hyperplane section of this convex body whose n-1 dimensional volume is at least 1/20 or some universal constant, which is independent of the dimension? So this is this looks like a very simple question, but apparently the answer is still unknown to this question. It is known that you can put some dimension-dependent constants in place of this C that you'd like to have, and the best known result right now is n to minus quarter, which is essentially due to Bourgain. There is an affirmative answer which is known for many convex bodies. For instance, for convex bodies with some kind of symmetries like coordinate symmetries, or for zonoids, or for their duals. Various models of random convex bodies were investigated, etc., etc., etc. But still, it's not clear if this question has an affirmative answer or if it's completely wrong. It was observed by Keith Ball, who is in principle here, but right now he's in Edinburgh, that it's a good idea to broaden the context and formulate the hyperplane conjecture in the class of low concave densities. So what is low concave density? Probability distribution on Rn is low concave if it takes the form e to minus h, where this function h is the exponent is convex. Okay, so low concave, e to minus convex function. And we also allow the function h to attain the value infinity just for convenience, which means that it has an obvious meaning. So low concave densities decay exponentially at infinity. And for instance, the Gaussian measure that you can see here is an example for low concave density. But also, if you take the uniform measure on any convex body, this is also a low concave density, which corresponds to the function h, which is, say, 0 or some constant on the convex body, but is infinity outside. There are many nice properties for low concave densities. So something which is pretty obvious is that if you take the pointwise product of two low concave densities, then you get, again, something which is proportional to a low concave density. There is a much deeper fact, which falls on the Poisson-Kaplan-Leonard inequality, which is that if you have any low concave random vector, and you apply some linear transformation t, for instance, you project to a certain subspace, you take only the first coordinate, then you again obtain a random vector which has a low concave density. Okay, so this fact is the Poisson-Kaplan-Leonard inequality, which is a functional version of the classical Bruin-Minkowski inequality. One should mention that. Actually, there is another reason to mention Bruin-Minkowski, or at least Minkowski, because this is his birthday today. So he was born 147 years ago. Exactly. Also, Frank knows someone who was born this day. Okay, so these are low concave densities, so stable under projection, under convolution, and things like that. Now let's consider the following strange parameter. So given a low concave density, I consider the something which I call the isotropic constant, which is the following product. You have two terms. One of them is the supremum of this density to power 1 over n. And the second factor is just the determinant of the covariance matrix of 4 to power 1 over 2n. And for some reason, I call this product of two terms the isotropic constant of the density rho. So it's not straightforward to verify that this number, the isotropic constant, is in a affine invariant. So for example, for all ellipsoids, you have the same number because of affine equivalent. But if you want to understand the meaning of this isotropic constant, perhaps it's a good idea to choose an appropriate line transformation which puts your measure in a good position, as we say. And I think one of the good choices of such a position is the isotropic position. So we select an appropriate linear map, a affine map, so that our random vector would have mean 0, and such that the covariance matrix will be the identity matrix. Of course, you can always do that if you have finite second moments and we have exponential tails, so no problem. Which means that all of our marginals have mean 0 and variance 1. Now, when our density is isotropic, the second factor is, of course, just 1, and we remain with the first factor, which is the supremum of the density of x to the power 1 over n. And there are many equivalent expressions to this supremum of the density. So, for instance, up to factor, say, 5, it is equivalent to the value of the density at the origin to the power 1 over n, or to a center expression. I think, is it the Renyi entropy? To the integral of 4 to the power 1 plus 1 over n, or to some power of the entropy, minus the entropy of the random vector x. So you see here is that we have an interplay between two quantities in the definition of the isotropic constant. We have one term which is the covariance structure of x, and we have the second term, this supremum, which is essentially an entropic factor, which is related to the entropy that x occupies in space.
The equivalence of these three guys, is it very simple? Or?
Yeah, I mean it's yes. I mean it's not. So the first, okay. So the first one is for Deleuze shows that it is to up to factor of e. For the second one, or the third one, you can just replace rho by some convex bodies. If you just look at the level set where rho is at least e to minus n times its supremum, then this has most of the mass in a very strong sense of the distribution. So whatever is outside is exponentially small in dimension. And if you restrict n to this convex set, then it's clear that there everything is the same, right? I mean, then rho to 1 over n is just a constant up to factor e in that set, and so all these things are the same. And that fact that you can restrict attention to this convex set, well, this, I mean, okay, it's known for 20 years, say. It's not entirely trivial, but okay. All right, so why did I introduce this isotropic constant? Because you may formulate the slicing problem using this constant. And actually the problem is the following. So is it true that the universal upper bound for this isotropic constant over any log concave distribution in Rn? I wrote isotropic, but of course, as I said, it's a affine invariant, so it's not important. We can assume it's isotropic. And again, I need to say something about the equivalence, why it is the same question. So basically, it's an observation. I mean, the main idea is an observation of Hensley, which says that you can relate the volume of hyperplane sections of a convex body, or of the integral of a log concave density, with the variance of this distribution. And there are a few other works. Nothing is really complicated. It's essentially simple things, which shows that this is an equivalence. Okay, so let's think of an example, because it's a bit hard maybe to imagine log concave density. So let's suppose we have a convex body K. And if we assume that we normalize it so to have a covariance identity, it means that the isotropic constant is just its volume to power minus 1 over n. Okay, so what this conjecture says, it says that the convex body should have large enough volume. If its covariance matrix is the identity matrix, it cannot have very little entropy. Its entropy must be large in a sense. If you want, you can look at the following picture and you can ask yourself the following question. Suppose you have a convex body which has the same covariance matrix as the Euclidean ball. You can even assume it is contained, say, in, I don't know, twice this Euclidean ball. And the question is whether you can arrange such a configuration with the convex body K having a much smaller volume than the volume of the Euclidean ball, and much smaller on a scale of e to the n at least. I mean, scale of, say, n to the n, or something like that, much smaller than an exponential scale. All right, and the slicing problem is that this is impossible, that because of convexity, if you have identity covariance, then the shape has to occupy a large portion of space. In other words, this conjecture, if you believe it's true, means that the covariance structure somehow, and the entropy are equivalent. So one determines the other, more or less. And of course, this does not have any sense unless you have some very regular assumptions such as convexity. Okay, so any questions so far? Okay, so some remarks. So it's not so hard to show that the isotropic constant is always larger than some universal constant. As I said, you know that the best bound is n to 1/4 for this isotropic constant. And there's a simple reduction. So the generalization from convex body to low concave measures does not make the problem harder, in the sense that the supremum over all low concave distributions is actually equivalent to the supremum only over centrally symmetric convex bodies. Okay, so let's discuss some of the way to obtain some bounds on this isotropic constant, upper bounds. I think that in almost all known bounds for the isotropic constant, one uses the logarithmic Laplace transform. There are bounds which are off by log factor, which do not use this, but for tight bounds, I think you usually use the Laplace transform. What's the idea? We have some random vector x in Rn, expected in Barrett center 0, Barrett center the origin. Then you look at log Laplace transform. So you look at the logarithm of the expectation of e to the x dot psi in Rn. So this is also the Komula generating function. It is a strictly convex function on Rn. It's infinitely smooth, real analytic. Since this is a probability distribution, its value at the origin is 0, and this is the minimal value. It's non-negative by n-sense inequality. And there is one good thing about this log Laplace transform, which is it helps relate the two objects that we care about. So we care about the relation between covariance and entropy, and indeed it's relatively okay. It's possible to extract from the log Laplace transform information about the covariance matrix of X and its the so-called tilts, which I'll explain in a minute. On the one hand, and on the other hand, you can get information about the entropy of X and volume of related convex bodies, which I'll discuss in a minute. Okay, so this is a stamp of Laplace. And there was a discussion, how could it be that the stamp costs 30 francs, which is 10 pounds or something? No, 3 pounds. Okay.
When was the stamp published?
We have no idea. Sorry?
I think this is ancient funds.
Ancient francs. Okay, maybe inflation was deflation. Okay. All right. Okay. So the Laplace transform, log Laplace. Maybe many of you know these things, but I'll discuss it slowly. So we have this function value. Of course, we have to differentiate it, otherwise it's not analysis. What's the best way to differentiate this function? To consider the so-called tilt. What's the tilt of the random vector x? You take your vector, a point x in Rn, and you consider the following density. So this is the original density, rho of x, times some exponential factor in the directions of psi. And this is not probability distribution, so you normalize, and you call this random vector that you obtain, this random vector with this density, you call it x psi. Actually, I put this tilde here because in a moment I'm going to center it. So tilde is the uncentered version of this random vector, and this is the tilt of x. You kind of tilt it, you push it in the direction of psi. And then it's very easy to express the derivatives of lambda in terms of x psi. Actually, the derivatives of lambda are the components of x psi. In particular, the gradient of lambda, of log Laplace, is just the Barrett center of x psi tilde, of this tilted distribution. The Hessian of log Laplace is nothing but the covariance matrix of this tilt. Now, I would also have to work with cell derivatives, at least towards the end of this talk. And this is, there's no, I mean, okay, so our name, this is somewhat complicated expression, which you can see here. And our way to avoid this complicated expression is to hide it in the notation of Riemannian geometry. So, but this is what lies behind what we're going to do. All right. So as I said earlier, I want to center my random vector. So the center tilt is just you take the xi tilde and you subtract the Barrett center, and now it has expectation 0. And a very important fact which I forgot to mention, so I go back one slide, is that the tilt is again log concave. So if our density rho was log concave function, and if I multiply it by some exponential factor, then on the exponent level I just add some linear function, and adding a linear function does not alter the log concavity. So those tilts are again log concave random vectors, which is a very useful fact. All right, so we begin with x. We construct this collection of tilts, which are again log concave and centered. Another nice thing is that the log Laplace of the tilt is a simple variation of the original log Laplace transform. So what you do to get the log Laplace of the tilt is just you subtract the tangent hyperplane to log Laplace at that point, and you translate things to the origin. So you get a nice convex function whose minimum is 0, and it is attained at the origin. It is just a linear transformation. I mean, just subtracting some affine function from the original log Laplace transform. Now, log Laplace and tilts appear in many places, but I chose to mention only one, which is Cramer's theorem, not on large deviations, but I like very much his moderate deviations theorem from 1938, where it's a very, very nice argument involving tilts. All right. So let's see what can be the use of this approach to convex geometry, and I'll begin with the with relatively relatively simple argument. Okay, not so simple, but with a relatively quick argument. So let's assume for simplicity right now that x is not any log concave distribution, but let's assume it's uniform in some convex body K in Rn. Now, recall that the gradient of log Laplace is the Barrett center of some distribution, which is just a tilt of the original distribution. In particular, the gradient of lambda, this Barrett center, must belong to K, because K is convex, right? The Barrett center of a distribution supported on K always belongs to K. And also, since this log Laplace is strictly convex, it means that gradient lambda is a one-to-one map. So we may apply the following change of variables formula. So the volume of K is at least, well, it actually equals, but we don't, okay, well, I wrote equals, but we just use the fact that it's at least. The volume of K is at least the volume of the image of log Laplace. Gradient lambda is one-to-one, so you have this change of variable formula. You get a Jacobian term, which is the determinant of the Hessian. And remember that we like the determinant of the Hessian because this is a covariance term. And actually, well, I'm willing to give away lots of the information and have a lower bound of this integral over entire Rn by something smaller, by the integral over the polar body to K times n. So I assume I don't have to define the polar body. Is it a safe assumption? Yeah, okay, good. All right, so we have this inequality, and let's just do something very naive. We can say that for most points in the polar body, the integrand is smaller than the integral divided by the size of the set. In particular, if you choose a random point in n times k polar, the determinant of the Hessian of lambda at that point is smaller than the ratio of volume of k to the volume of k polar. All right? And this determinant of Hessian is the determinant of a covariance matrix, which means that we got an upper bound for the determinant of the covariance matrix of the tilt. And I just use some simple facts. So for example, since xi was in n times k polar, it means that we didn't change the density over k by much by adding this exponential factor. This exponential factor is roughly, is between e2 minus n and e2 plus n. So it means that the super of the density did not change at all. Therefore, the new isotropy constant, it is a product of two terms. As you remember, there is this entropy term, which was the volume of k to 1 over n. This does not change at all because we have these bounds, times the determinant of the covariance matrix, for which we have this upper bound. And if you arrange things a little bit, you conclude that the isotropy constant of the tilt is bounded by 1 over the so-called this volume product, the volume of k, times the volume of k polar times n. Right, what can you do with this volume product? There is a well-known bound of Bourget and Niemann, which says that the volume of K times the volume of K polar is at least a constant to the n. And what you conclude is that for most choices of a point psi in the dual space in n times the polar body, the isotropy constant of x psi is bound by a constant. So for most tilts, in the sense that you choose the tilt randomly in the dual unit in the polar body times n, the isotropy constant is bounded.
I don't understand.
Yes.
You mean most?
Most. Okay, so I'd say there. Okay, so here I said there exists, right? But I'm willing to give a factor of e to the n. I don't care if there's a factor of e to the n here, because it goes, when you see it goes with this power later on. So most means that a fraction of 1 minus e to minus n.
Of nk polar.
Yes, because by Markov inequality, yes. Okay. Now maybe it's better to formulate this fact about tilts in the language of convex bodies. And as I said, there is a correspondence between low concave distributions and convex bodies, which is due to Keith Boyle, and it's based on Boozman's inequality. So Keith Boyle defined this convex body in Rn, and the convexity of this convex body is precisely Boozman's inequality. So this is a convex set. And as it turns out, as you can see from this formula, it is somehow it relates very much to integration in polar coordinates, right? This convex body has the same radial projection to the sphere. Okay, if it was n minus 1 and not n, this convex body would have the same the unit formation of this convex body would have the same radial projection to the sphere as the original distribution. So it is basically arranging I mean, it has very related mass distributions to the density F, and almost all parameters that you can think of are the same for F and for Kf. And in particular, the isotropy constant of F is the same as the isotropy constant of Kf. So if you apply this construction to x psi, so x psi is the tilt of say the original convex body K. It's a density distribution. You take this body of Keith ball, you get another convex body T. It has the same isotropy constant as the original x psi, so it's bounded. And also, it's not very hard to show that the tilt that we did does not change the geometry of the convex body too much. This is because x psi is not very large. In particular, I deduce the following theorem, that whenever you have a convex body K in Rn, you can find another convex body T in Rn, which is not so far from K. So it's 1 minus epsilon times K is contained in T, and T is contained in 1 plus epsilon K. And the isotropy constant of T is bounded in terms of epsilon solely. So just a constant over square root of epsilon. So of course, everything is dimension independent. All right. So and the key. So why was it so a good idea to use the log Laplace transform? Maybe I'll go back to slides. So if you look at this formula, on one side we have the volume of K, which is related to the entropy of K. And on this side, we have some integral of covariance matrices, of determinant of covariance matrices. So this identity relates covariance matrices and entropy, which is the subject of the object of our study. All right. Okay. So now let's continue to discuss what other tricks can be done with this logarithmic Laplace transform. So first of all, it has lots of many properties that may be proven via one-dimensional arguments. And these one-dimensional arguments are usually of one of the following two kinds. The first option is to do the following thing. So take subspace E in Rn. Now if you look at the projection of X onto this subspace E, it has log Laplace transform, which is exactly the restriction of the original log Laplace to this subspace E. Right? I mean, okay, I identify the space and its dual, but we know that Fourier transform, Laplace transform so taking the push forward of the measure corresponds to taking the restriction to the subspace of these transforms. Now, the good thing about the projection of X onto E is that by Prekopa-Lender, this is low concave again. This is stable under low concave distributions. And if E is of dimension 1, for instance, you get that the restriction of log Laplace to any line, actually, is the log Laplace of some one-dimensional log concave distribution. And log concave distribution in one dimension is the simplest object in the world. I mean, it's a very rigid class of distributions, and it's very hard to ask question about it, which is you cannot compute at least up to, say, a constant or something, or at least say up to some number. And actually, it's a compact space, so maybe it's anyway. Okay, compact space when you fix the Barrett-Center and the variance. Anyway, so this is one trick that you may apply. The second trick is to integrate in polar coordinates and use the Laplace method for integrals of this form, of integral of the form t to the n minus 1 times the log concave function. And log concavity is precisely the condition that guarantees that Laplace method will work. That most of the mass of such integrals indeed come from one point, which is comes from a very small region in the real line. All right, so these two things may enable us to prove some properties of log Laplace, which are not very complicated, not very deep. And now I'm going to describe them. So I'm interested very much in the level sets of the Laplace transform of log Laplace, and I denote by lambda smaller than t the level set of log Laplace. And I'll also have to consider the symmetrized level set, which is just the intersection of the level set with its minus. So, for instance, using these one-dimensional arguments, one may show that the nth level set of log Laplace is just the polar body times n. And this sign here means that these two convex bodies are equivalent up to a factor 5. So this convex set is contained in 1/5 of nk polar and is contained in 5 times nk polar and contains 1/5 of this nk polar. And in particular, if you know that the level set of log Laplace is approximately an ellipsoid or Euclidean ball, it means that k polar is approximately an ellipsoid, so k itself is approximately an ellipsoid. And for ellipsoid or for Euclidean balls, we know the slicing problem, so you know that in this case, the isotropic constant it will be bounded. And another thing is that we can now add another formula for the isotropic constant. So this supremum over we had two terms in this isotropic constant. We don't touch the Covance term, but when you look at the other term, well, now you can put the volume of the nth level set of log Laplace. And it is equivalent to the supremum of the log curve distribution up to these factors. Okay, and so for example, you can just, what's good about this approach? For instance, just from the simple fact that the isotropic constant is bounded from below, you can get some lower bound for the variance. You can get the following corollary is that whenever you have, you can get that there always exists at least one direction, such that the variance in this direction is at least the volume of the level set of this Laplace transform. And this is, of course, true for any subspace that you take of your distribution by this principle I presented. So, for instance, you get that if you know that the level set of log Laplace are small, this is what you want to show. That if the level set of log Laplace are small, then you have large variance, at least in one direction, for instance. Okay, so let's, before continuing to develop this theory of log Laplace of log curve distributions, let's compare this approach to an equivalent approach, which is using the LP centroid bodies. This approach was developed by Paris with lots of success, and here we consider, instead of considering the Laplace transform of the expectation of e to the x times theta, we just take the LP norm of theta. Of course, these things are very much related, but somehow this gives some insights that log Laplace does not give, and as we'll see, also vice versa. So each point of view has some advantages over the other point of view. This expression, the expectation of the moment, the LP moment of distribution, it's a convex function, so it is the supporting function of some centrally symmetric convex body, and we denote this convex body by ZP of x. This was the definition of Luttwak and Zhang in the 90s. When P equals infinity, and K is centrally symmetric, what would you get? When P equals infinity, the L infinity norm is just the width in the direction of theta. So H Z infinity of X is just the supporting function of the convex body K itself. And you'd get just ZP would be just the support of your measure, or the convex body K itself. So as it turns out, the ZP bodies, the LP centroid bodies, are equivalent to the duals of the level set of log Laplace, or more precisely, for any p greater than 1, the LP centroid body is equivalent to p times the polar body to the symmetrized level set of log Laplace. What's written here? Okay, so you could say that you can switch point of view whenever you like, and this is indeed true. Now, one advantage of working with ZP bodies over the dual levels of log Laplace is related to the mean width. There are some, there is a very simple formula for the average, for the LP average of the supporting function of ZP. Yes.
Slide depends on P.
Sorry?
Just the previous slide.
The previous slide? Yes? Equivalence is, no, it doesn't depend on P. No, if I write this sign, it always means just up to constant universal factor. I will not suppress any depends on anything in these things.
Because when P tends to infinity, on the left-hand side you have K, basically. No?
Yes.
If X is...
Yes. Yes, so it's nice. So what's the what is the level? So log Laplace is symptotic to supporting functional at infinity. So when P goes to infinity, it's a good example. So when P goes to infinity, the level set of log Laplace is roughly P times K polar.
Okay.
So you get P squared. No, you don't get P squared because P times 1 over P times K polar. So you get, yes. Okay. Right. So I mean, there is the following expression. If you've never seen this widths of convex bodies, what they mean, maybe you will not appreciate it. But these widths appear in many places, especially in Dvoretzky's theorem. And there is a very simple formula for the LP mean widths of the centroid bodies. So you just exchange. I mean, if you take the LP, you have a formula for the supporting functional. You take its p power. It will be just some integral of x dot theta to the power p. If you take the average over the sphere, you'll get just some moment of the Euclidean norm of p. And if your body is isotropic, you get that this is always at least square root of p. So you get for free some estimate for the mean widths, the LP mean widths of ZP. And of course, it translates to something about the dual levels of log Laplace, but I mean, directly, it's really hard to prove it for log Laplace. A posteriori, you could argue that, well, you can, but I mean, you can certainly not, will certainly not come up with this idea if you just work with log Laplace. Okay, now, as I said, this LP mean width is very much related to Dvoretzky's theorem. And this comes handy in the following approach of Paris. So Paris defines a certain parameter of a local distribution called Q star. And this is the following parameter. You take the maximal, say, integer p, such that if you take a random section of dimension p of the level set of log Laplace, you get approximately a Euclidean ball. So what's the rationale behind these parameters? There are two things that go about it. So first of all, as we said, if you know that level set of log Laplace is approximately Euclidean ball, you know many things. I mean, you know that this is approximately the polar body, so you know that for instance, the isotropic constant is bounded. So this is a good thing to have. And also, it's a good idea to have the same number p here and here. So you take the p level set when you consider p-dimensional sections, because we have a very good understanding of the nth level set in Rn. The nth level set is essentially, say, the polar body, as we said. So Maybe this is the intuition behind this parameter Q star of Parvis. And now, the proof of Vitali minimal of Vorotsky's theorem from the 70s had a formula for the dimension in which random sections of a convex body are approximately Euclidean. And this formula is very much related to this LP mean width. And if you use this formula, and of course many other tricks, then you get two interesting things. So you get that the LP moments of your random vector, of the Euclidean norm of the random vector x, do not change much between 1 and Q star, this parameter Q star. This is one thing. And the second thing that you get that Q star is always at least square root of n. Now this is quite striking. This was the first result in which you saw that moments, I mean, the L square root of n moment of the Euclidean norm is the same as the L2 moment. It's really remarkable. Okay, now what else follows from this approach of Parvis? So we said that you know that if you take the random section, it is approximately Euclidean ball, for which you know there's a entropy constant, and therefore you can get some relation between covariance matrix and volume of level set just from knowing there's a entropy constant. Okay, probably it's pretty hard to follow on this inequality, but I'll just say that you get some upper bound on the level set of lambda, but only up to level set, only for level set which are up to this Q star. So if you look at level sets of like log Laplace for k smaller than Q star, you have a very good understanding of them because their sections are Euclidean balls, so they sort of behave like your measure, as if your original measure was Gaussian, say. But after this Q star, the level sets may behave differently. Okay. Now let's see. Let's go back to this approach of looking at the derivatives of log Laplace and consider these tilts. Now, as I said, there is a close relation between the log Laplace of the tilt and the original log Laplace of the distribution. In particular, if you take psi, which is not too far from the origin, they have the same level set. Okay, so if psi is in the symmetric level set of order p, then the level set of the log Laplace does not change when you move from x to x psi. And this is good because it means that if you have any parameter which depends only on the level set of log Laplace in a nice way, in a way that respects this equivalence, then it will be the same for x and for x psi. Okay, so the tilts, they might be a bit far from x in some senses, but if you have some parameter which depends on your level set of log Laplace, then this parameter will be the same for x and for x psi. And for instance, if you know that the tilt belongs to a level set which is below Q star, okay, then the Q star of the tilt will also be, the Q star will not change if you take, I mean, the minimum of P and Q star of X is the same for X and X psi, which is interesting to know that the tilt has the same Q star in many cases. In particular, so earlier I had some lower bound for X, for the variance of X in terms of some things, and now I can change it to X psi, because that lower bound had only the volume of the level set, so now we can get some lower bound for the variance of X psi in some direction. Good, so we found a way to translate some information about the level set of Laplace transform of X to lower bound on covariance of X psi. Now, we actually want to understand the determinant of the covariance matrix of X psi, and not just the existence of a single, direction. And for that, you cannot continue to work with Q star. You need to go to another. You need to use another parameter, which is stable under projection, under marginals. Q star is not stable under marginals. So define a new parameter. We call it Q star G sub h, and you get that after this parameter, you can actually say that for any point in the level set of Laplace transform, which is up to this parameter, the determinant of the covariance matrix is very large, at least a constant to power n. Okay, and this is good because remember that we had this change of variables argument before, which says that the entropy of K is the integral of this determinant of covariance matrix. So you get some low, you hope from this thing you get some lower bound on K. All right, so we can apply this transportation of measure arguments that we had before. But there are also some refinements which I think are pretty nice to mention. So these tricks are really simple, but they are not as well known as they should be to people working with convex functions. This is the fact that gradient images of convex functions are a very simple object. For instance, if you have suppose you have any convex function in Rn, which vanishes in the origin, take the piece level set of this convex function, take its image under the gradient map, then what you obtain is roughly the polar body to this level set, up to this factor of p. Of course, once you write it down, it's very, very simple to prove. Now you may use this fact to get, say, some estimates on integrals of the determinant of Hessians on the convex body. And for instance, if you want to compute the integral of the determinant of the Hessian of f on the piece level set of f, then this is exactly, by change of variables, just the volume of the gradient image of this level set. And the gradient image of the level set is equivalent to it's the polar body approximately, so it's equivalent to the polar body to f. Now I said that a little bit of cheating. Cheating is just this factor half here. So actually, if you want it to be, if you want it really to follow from here, then you need to change p a bit. So it's smaller than or equal. It's smaller than or equal. It is larger or equal than what you see here, and it's smaller than equal. The same thing with p over 2, for instance. But approximately, it's, I mean, if the function f is not too wide, this thing is correct. And if you use the fact that the volume of the polar body to power 1 over n is determined by the volume of the set itself, you get, for instance, the following nice formula, which says that the integral of the determinant of the Hessian actually determines the volume of the level set. If you take the average of the determinant of the Hessian of a function of a level set, then you get p over the volume radius of the set squared. And the volume radius is just the radius of the Euclidean ball that has the same volume as our original convex set. So this might be confusing if you're not used to it. So let's take an example. Suppose f is just the Euclidean norm square over 2. Then its determinant of the Hessian is just 1. And indeed, the volume radius of the piece level set is indeed square root of p, as is predicted by this equivalence. All right, so let's summarize what's the general strategies that we're doing. So what we said is the following, that we know to control things up to q star, or well, some variation of q star gh, what I call. And when x is isotropic, you have a lower bound for a determinant of the Hessian of lambda for psi in a level set up to this q star. This lower bound of the determinant of the Hessian, by the formula I just had, that the average is p over the volume radius, translates to an upper bound for the volume radius of the level set of log Laplace. And this is equivalent to an upper bound for the isotropic constant. So you conclude the following theorems, that the isotropic constant is at most square root of n over this q star thing. Okay. Now, I keep telling you about this parameter q star gh, but what it's meaning? What is its meaning? So its meaning is the following. It's actually the geometric average. It's sort of a geometric average of the growth of the LP norms of linear functionals on the convex set. We know that since x is a local invariant norm vector, we know that the expectation that for any unit vector theta, or for any vector theta in Rn, the LP moments of x dot theta go at most linearly with the dimension. This is some classical consequence of Minkowski follows from Berwald work, for instance, in the 40s. So I define delta x of p to be the supremum over all directions of the LP moment of a linear function of x. And now this Q star is going to be a certain geometric average of this growth of this worst possible linear functional. Now, what's good about this parameter? The good thing is that if you know that the marginals of your distribution are better than sub-exponential, if you know, for instance, that they are sub-Gaussian, this parameter gets better. In particular, if you have a random vector which is what we call psi alpha, which means its tail is like e2 minus t to the alpha, then you know that the LP moments grow slowly in some sense, this way, and you get some bound for Q star GH. In particular, if you just apply it to the theorem I mentioned with Immanuel Millman, you get an upper bound for the isotropic constant of the following forms, that it's most n to 1 minus alpha over 2. So for instance, if alpha equals 2, you get that it's bounded by just the C2 constant. And this improves a bit some earlier results due to Bourgain. Bourgain had some additional log factor, and Daphne Sparrow said the square root of log factor there. Okay, so this is all about this interrelation between the slicing problem and this approach of Paris. Okay. Yes.
So you say then Q star GH is approximately the same?
Yes.
If I remember well, Q star GH was a kind of Paris Q star, but with an inductive stuff.
Yes. It's more. It is smaller than Q star. Yes, it's smaller than Q star.
But what is written after then? I mean, it's not. It's a theorem. I mean, it's not obvious.
It's not. Yes, I mean it's you need to prove that. Yes, sure. It's not obvious, right? I mean, yeah, right. So maybe I'll say a bit.
For instance, when you see this, then you immediately get the T-sat6.
Sorry.
Root n, you from this it follows that Q star is at least root n for something that's isotropic and not concave, right? Or not? Because on the right hand side you find something like
sure. Yes. Yeah, it's a good observation. Right. Yes, it follows. Yeah, right. From here you can easily. Yeah. So Q star. Yeah, this is a lower bound for Q star of x.
Proving that Q star is bigger than root n is something. I mean, hard or not so easy.
I don't think that it's going to be a shorter route to proving that Q star is least square root of n, because it involves the same chain of ideas.
Sure that was not something.
Yes, it's not obvious. It's not obvious. It's not. Yes, it's not obvious when you write it like that on a slide. But it's true indeed. Yeah. From here you see just from fact it's psi 1, you get that it's least square root of n, and this is a lower bound for Q star. For Q star, right? Yes. Further questions? No. Yeah. Okay. So let's slow gears again and discuss a different problem. There are other problems in high-dimensional convex geometry which are not solved. And I want to discuss something related to the central limit theorem for convex bodies. Okay, so we have the following theorem. Suppose you have a random vector x in Rn, which is isotropic. I mean, isotropic means that covariance matrix is the identity matrix. Then as it turns out, most of its mass, most of its volume, is actually concentrated on a very thin spherical shell. So if you look at this picture, there is a thin spherical shell, whose width is very, very small compared to its radius, and 99% of the measure of this convex set is actually contained in this thin spherical shell. Okay, so this was a conjecture by Antilo Bolpe-Usinaki in this form. There was a related conjecture of Bremen-Fucht. And it is true. And the interest in this conjecture stems from earlier work of Sudakov and Diakonis and Friedman, which says that whenever you have such a phenomenon, whenever you have a distribution in high dimension, which is say isotropic, I mean this normalization is not really important, but let's say it's isotropic, such that most of the mass is indeed concentrated very close to a sphere of a certain radius, which must be square root of a normalization, then you have a central limit theorem. Then you have lots of Gaussian marginals. Okay, a random projection will be approximately Gaussian. So this was the interest in this problem. But we right now don't care about this Gaussian approximation directly, but only about this width of the spherical shell that captures most of the mass of a convex body. So this width of a spherical shell that captures most of the mass is related to the degree of approximation in the central limit theorem for convex sets. And we define the following parameter, sigma n. So sigma n is just the variance of the Euclidean norm of x over the when you take the worst possible log concave distribution in Rn. So let's look at this picture. We know that since x is isotropic, we know that the Euclidean norm of x has expectation roughly square root of n. So in order to show that the width of this spherical shell is much smaller compared to its radius, you need to show that sigma n is much smaller than square root of n. Okay, so square root of 1 is the trivial bound, and whenever you get something below trivial, you get a very thin shell, which is enough for Gaussian marginals. Okay, what's known about this parameter? What is known about this parameter sigma n? The best upper bound to date is due to Gedon and Millman, which is n to 1/3, and this improved upon previous bounds. A previous bound of Bruno-Fleury, which was n to 3/8, which was an improvement of some bound of myself, which was n to the 2/5 with some log factors, which, I mean, okay, there was some change of, and the original bound was it was just a little bit below square root of n. So we have these two parameters. We have the isotropic constant, which we know is most n to quarter, and we have the sigma n, where we see this gradual improvement over the years. And the next theorem, which will follow from this log Laplace approach, would be a joint theorem with Ron and Eldan, which says that this isotropic constant is at most a constant times sigma n. Okay, this is related to a result announced by Skis-Ball, in which you replace sigma n by another parameter, which is bigger, which is the spectral gap. And actually, I think the dependence there is actually worse, it's exponential, but maybe, okay. I think right now this argument depends on exponential. Okay, so how much time do I have?
5 minutes.
5 minutes, okay, good. Okay, so maybe I'll explain a bit about the proof of this result. Yes, it was a good point to ask what is the time. Right, so I'll try to do it as gently as possible. It turns out, okay, you have this log Laplace, we keep talking about the Hessian at each point, the convex matrix at each point. It's a positive definite matrix at each point in Rn. Natural thing to do, just think about this as a Riemannian structure. Actually, there is an even more natural, which is looked at as the Keller structure, but this is not for today. Now, what's good about this Riemannian structure? The good thing is that this definition is a fine invariant. It does not depend on the Euclidean structure. Whenever you have any linear space, without any, and you have log concave distribution in this space, you immediately get such Riemannian structure on the dual space. Okay, and you can write a formula which is coordinate independent of the structure for this Riemannian metric. Okay, so we have some Riemannian structure which is finely associated with this convex body K or measure mu, which is a good thing to have because we like things which are fine invariant in this business. Well, you can have some computation. As it turns out, the sectional curvatures are uniformly bounded, and in many cases they vanish. For instance, if your random vector is a product measure, then they vanish. But I mean, I was not able to make any sense of curvature in this context. And the good thing is that many computations simplify in the presence of this Riemannian structure. So, for instance, suppose I want to compute the Riemannian gradient of some function which is the logarithm of the determinant of the covariance matrix of x. All right, this seems complicated, especially after we saw the third derivative expressions. But if you remember that your metric does not depend on the Euclidean structure in the original space, it means that you can pretend that xi is isotropic when you compute this expression. And after you do, and if x is isotropic, it means that many things simplify considerably. And you can get very simple formula for this gradient of log determinant. I just wrote the upper bound, but actually even the expression could fit on this line. I mean, on this line, it's a simple expression. In particular, you get some upper bound for the gradient for the change of the determinant of the covariance matrix. Okay. Now let's assume that x is isotropic. So say the origin, its covariance matrix is determinant 1. If you have some if we know that this log determinant is a Lipschitz function, right? I mean, with this parameter, it means that the determinant does not change too quickly. And if you look at the Riemannian ball of radius, which is square root of n over sigma n around the origin, in this Riemannian ball, we pretty much control the determinant because it was a Lipschitz function. All right, and recall that what we want to have to bound isotropic constant is lower bound for the integral of the determinant of the covariance. And the question that remains to be answered is how big is this Riemannian ball of a certain radius around the origin? And there is some lemma which says that this Riemannian ball is big. In fact, it contains a certain level set of the Laplace transform. It's not very hard to prove. You just inspect the Riemannian length of the segment from 0 to xi, and this Riemannian length is bounded by some way by the Laplace transform. And therefore, you get some bound, which is the proof of that theorem when we're done. Okay, so I thought that my lecture would be before the tea break, so I made a slice of a tea kettle, but I was wrong, and the tea is already gone. So
You can have tea.
you can still have tea?
Everything.
Good. Okay. All right. Thanks.
So, are there other questions? Okay, thanks again.